Welcome to College Algebra. In this lecture video, we are going to continue with our lecture video series of chapter 4.2. In this video, I want to talk to you a little bit about the remainder theorem and what is so-called the linear factorization theorem. So let's take a look at the remainder theorem real quick. I kind of mentioned this on the previous video. The remainder theorem says if a number c is substituted for x in the polynomial function, then the result of f of c, that means if I substitute c into the function, okay, the result of f of c is the remainder that will be obtained by dividing the function by x minus c. So what that means is this. Let's use an example we done on the last video. Let's give this a try. When x to the third plus 3x squared minus 14x minus 5, when this, okay, let me take it to this page. All right. When this polynomial, let me scratch this off, is divided by x minus 3, the remainder, what we come up with was 7. Okay, let's go back to this problem one more time. All right, remember the remainder was 7. Then by the remainder theorem, what it's trying to say is we can actually plug in 3. Remember now, 3 was what I used as a divisor in the synthetic division. We can plug in 3 for x into the function. What comes out will be the remainder 7. Okay, so for example, let's take a look at on the calculator. If I was substitute 3 into the function, that will be parenthesis 3 raising to the third power plus 3 times 3 raising to the second power minus 14 times 3 minus 5. Remember, when we normally plug in a number for x into the function, what comes out is the y value. So what this remainder theorem is, when we substitute a number for x into the polynomial function, this answer also represents the remainder. Okay, also represents the remainder. So what we really want is to have 0 for the remainder. Whatever number we use to go through synthetic division with, what we want is to have 0 for the remainder. Because if the remainder is 0, okay, if the remainder is 0, that means the number you plug in is actually one of the zeros of the function. Okay, it's actually become one of the zeros of the function. So I kind of began to mention about the remainder theorem last time to you a little bit on the last lecture video series. Okay, so when for this example, we did, when I used a 5 to go through the synthetic division, the remainder was 0. So what that tells me is 5 is a 0 of this polynomial function. Therefore, x minus 5 would be the factor, okay, to the polynomial. It's one of the factors. Okay, 5 is also one of the zeros. Because ideally, 3x to the 5th power, when the degree of polynomial is 5, what that means is I should have 5 zeros, okay, to the polynomial. So for this example, so far I already know 1 once I see the remainder equal to 0. Now what will happen if I will go to my graphing calculator and graph this function? This is x to the 3rd power. So by the leading term test, I should have right side goes up, left side goes down. So when I graph this polynomial function, x to the 3rd plus 3x squared minus 14x minus 5. Okay, what I expect to see is something look like this. Okay. So it's coming from negative infinity, go all the way up, and then somehow curve back, and then go over this one right here. So I should have 3 zeros. So right now what I notice is 1, 2, 3. It crosses over the x-axis 3 times. So here are my 3 zeros. But I still don't see this. Okay, what I still do not see is y value equal to 0. Because the 3 we use is actually not a 0 to the polynomial function. So if you will graph any polynomial that we done before where the remainder says 0, you will see the number you use for the synthetic division, the y value will be 0. Okay, so we still got a lot of stuff to learn before we can truly finding the zeros of any polynomial function. Alright, so this example, use a synthetic division to determine if the given value for k, this number, is a 0. Is this number a 0 of this polynomial or not? If not, we can determine what's p of k. So rather than actually perform a synthetic division, okay, what we can do is plug in this number into this function and see what it come out to be. If it's 0, that means k is a 0 to the polynomial. If it's not, then I will know what p of k is still. So let's plug in 3 for my x. Alright, I can actually write this whole thing out, put it in the calculator, or I can actually graph it. So I'm gonna graph it for this one. Rather than substitute 3, I'm gonna just go to my table in a minute to see what the y value is, because the new y value will be the remainder. It's also representing the remainder as well. 7 x to the third 2 to 4 minus 7 x to the third minus 9x squared plus 4x plus 2. Okay, this is to the 5th power. So my graph will look something like this by the leading term test. Right side goes up, left side goes down. And here it is. Okay, the reason why I graph it so I can show you, even though I supposed to have 5 zeros, on the graph it only indicating three of them. Cross over the x-axis 3 times. So when I cross over 3 times, that tells me that the multiplicity on the factors of for these 3 is going to be 1, because even multiplicity means the function will turn at those x-intercept. They actually cross over. So out of the 5, I still got 2 missing. So how do I find the other 2 missing zeros? And that's where the section 4.3 will comes in. So just for this problem right now, I'm going to go to my table and see what x equal to 3. My y value is negative 121. So that's my remainder. It's not a 0, so that tells me that the 3 is not a 0 to the polynomial. Okay, and we will talk more about these remainder theorem as well when we go into the next section 4.3. I want to wrap it up this video, talk to you a little bit about something called the linear factorization theorem. Linear factorization theorem is basically saying for any given polynomials, we can write its factor in linear form. That means all the exponent can be written as to the 1st power. For example, if I have a polynomial function x squared plus 4x plus 4, if I will factor this polynomial, I can get x plus 2 times x plus 2. So if you look at it, all the exponent on the outside of the parenthesis is 1. So I can write them as linear factors. Every polynomial can be written as linear factors. Maybe they are not factorable, but you can still write them as a linear factor. Now, this we can take a step further and say this is x plus 2 whole thing squared. So that means I have an even multiplicity on my factor. So by the even and odd multiplicity, I know that when my graph reach -2 for x, it will actually turn. Okay, it will not cross over. So linear factorization theorem, okay, where we can write them as linear factors. C1, C2, C3 all the way to C sub n are complex number. Possibly can be real, not necessarily distinct. In other words, an nth degree polynomial can be expressed as a product of a non-zero constant, and we can have up to n linear factors, where each linear factor has a leading coefficient of 1. We can actually make all the leading coefficient on the factor to be 1 as well. Okay. Now, I put this theorem up here so we can actually do some of these examples. Construct a polynomial function with a stated property. For example, a 4th degree polynomial. That means the highest exponent will be 4. And I only have a single zero of 1. So my x is equal to 1. So what we're going to do here is construct an actual polynomial function based on what the degree of polynomial is and the zero they're giving me. So let's go back up here what I wrote. If I want to find the zeros of this polynomial function, I factored it, set each factor equal to 0, and solve for x. So basically what's going on now is I give you the answer. We now need to work backwards to the very top what the actual polynomial is. Okay, with the stated property. So by compare what I just wrote up here to my problem, okay, given an answer x equal to 1, so where was this 1 at before it was on the right hand side? It was actually on the left side where x is. So if I go backwards, that would be x minus 1 equal to 0. Remember, I have to set my factor equal to 0 before I can solve for x. So where was the factor at before I set them equal to 0? They were written in linear factor form. So that means my function f of x, my polynomial function, is x minus 1, written in factor form. But what's my exponents here? Well, my degree is 4. I only got 1 0. How can I have 4 degree only 1 0? Because my multiplicity is even. That's why it only show 1 0, because they actually have an even multiplicity. So that means the graph will turn at x equal to 1. So after we write out in factor form, now we just need to multiply this out. So x minus 1, I'm going to write it out this way. I'm going to say x minus 1 whole thing squared times x minus 1 whole thing squared. Split up into squared. Because now what I see is x minus 1 whole thing squared using the perfect square binomial property. as you can recall, a minus b whole thing squared is equal to a squared minus 2ab plus b squared. Alright, so x minus 1 whole thing squared, what I can do is to follow that formula. So that will be a squared minus 2ab. 2 times my a times my b is 2x plus my b got to be squared. That will still be 1. And this second part is going to be the same thing. X squared minus 2x plus 1. Alright, I'm not quite done yet because I still got one more multiplication to do. So now I'm going to multiply my polynomial out. X squared times x squared, negative 2x, positive 1. That should give me x to the 4th minus 2x to the 3rd plus x squared. Alright, negative 2x, do a distribution. Negative 2x times x squared, negative 2x to the 3rd. Negative 2x times negative 2x, positive 4x squared. Negative 2x times positive 1, negative 2x. Alright, positive 1 times these three terms back here, positive x squared, negative 2x, and positive 1. Alright, combine like terms. So x to the 4th, still x to the 4th. Let's see. Third power go next. Negative 2x to the 3rd minus 2x to the 3rd. Negative 4x to the 3rd. Alright, x squared. 1x squared plus 4 more x squared plus 1 more x squared. That will be positive 6x squared. X to the first power, negative 2x minus 2x, negative 4x. And my last term, still positive 1. Alright, so far this is my polynomial function. However, though, there's one more property. Oh, excuse me, there's no more property right here for this one. So it's just saying 4th degree and a single zero. So that's it. So this is my answer. Okay, so I multiply it out. Now, this example also on your homework, a little bit strange. 3rd degree, sorry, 3rd degree, so the highest exponent is going to be 3. It gave me my 3 zeros, because when the highest exponent is 3, I should have 3 zeros. X equal to negative 4, x equal to negative 3, and x equal to 1. But then after that, it says we're also going to end up with a y-intercept of negative 10. So let's take care of this toward the end, okay? Let's just kind of multiply this thing out, see what my polynomial is based on these 3 zeros. Then we can take a look at how we can deal with that negative 10. So same process. Move these terms to the other side, and then once I move them, those on the left side were the factor. Okay, so basically I can go ahead and say this is f of x equal to negative 4 come over, become x plus 4 equal to 0. Now we write them back as a factor form. This come over, become x plus 3. And the last one is x minus 1. Alright, let's multiply this thing out. When we multiply, we can only do 2 at a time, okay? So 2 terms times 2 terms, we can use FOIL methods. first thing I do for FOIL method, x times x, which is x squared. Last thing I do for FOIL method, positive 4 times positive 3, positive 12. So I'm using a little shortcut here. Just kind of do it by looking at it. Alright, my middle term is your inner and the outer combined. So that will be 3x on the outer, 4x in the inner. That will give me positive 7x. Alright, so the first two multiplied together is this. Now we'll multiply by the x minus 1. So let us continue. Alright, x squared times x to the third. X squared times negative 1 is negative x squared. 7x times x, 7x squared. 7x times negative 1 is negative 7x. 12 times x, 12x. And the last thing I should have, negative 12. If I combine like terms here, I should have x to the third plus 6x, right? Negative 1 plus 7 and positive 6. Negative 7 plus 12, positive 5x minus 12. So this could be my answer if I do not have this little last bit of property. So how do I handle that last little bit of property? Let's think about this. What does y-intercept with negative 10 means? That means when the graph crosses over the y-axis, okay, that point is the y-intercept, where x is equal to 0, y is negative 10. Alright, so now I'm going to use this theorem. This theorem at the very beginning has some sort of leading coefficient that has been factored out, where all these coefficients in here can be 1. All these coefficients in the factor form can be 1. So what I got myself so far is some sort of leading coefficient out here times the entire polynomial, okay, is equal to my function f of x. Now I'm gonna write it down, okay? So f of x also represents y. So my y is negative 10. So that means negative 10 can equal to this leading coefficient of some sort times my entire polynomial. So when does the y equal to negative 10? It equals to negative 10 when all the x values are 0. So imagine if I plug in 0 for all these x's here. When x equals to 0, y is negative 10. So only thing left here is going to be my negative 12. So negative 10 equal to s of n times negative 12. If I want to get s of n by itself, I would divide both sides by negative 12. So s of n equal to negative 10 over negative 12, which is positive 10 over 12. And if I reduce it, that would be 5 over 6. So that means I would need a leading coefficient of 5 over 6 to end up with the y-intercept of negative 10. Because my original one, after I simplified, the y-intercept was negative 12. So how do I make this y-intercept negative 12 into a negative 10? By a factor of 5 over 6. So that means my actual function is going to be 5 over 6, which is going to be right here, multiply every one of these terms. So what's 5 over 6 times x to the third? 5 over 6x to the third. What's 5 over 6 times 6? Positive. Oh, sorry, this would be x squared right here. It will be positive 6x squared. Excuse me, positive 5x squared. was 5 over 6 times positive 5x, positive 25 over 6x. And what is 5 over 6 times negative 12? 6 and 12 cancel out into 1 and 2. So negative 2 times 5, negative 10. That's how I end up with the y-intercept negative 10. And that would be my answer for the actual polynomial function based on the property given. Alright. Now one of the toughest one to multiply it out is probably like this one. Degree is 3, and now this time I have zeros. That is 2 minus I, another 0, 2 plus I, and then last 0, x equal to 2. Alright, we'll deal with this leading coefficient negative 4 just in a minute. Alright, so what's going on here is sometimes my zeros can be rational number, sometimes my 0 can be non-real numbers as well. So we can write them as a linear factor. So I'm going to move all these terms on the right over to the other side. So that means I should have x minus 2 plus I equal to 0, x minus 2 minus I equal to 0, and x minus 2 equal to 0. Okay, so now write them back as a linear factor. So where's my a sub n when I write these as a factor? I'm assuming to be 1 for a moment, okay? So if I write them back out, it'll be x minus 2 plus I, x minus 2 minus I, and then a x minus 2. So what you see here is this thing look just like the linear factor theorem that's above. Coefficient is all 1 in the factor, where the C, C1, C2, C3 are complex numbers. Sometimes they can possibly be real or not necessarily distinct. Okay, so I'm basically rewrite my problem as in this form and treating a sub n right now as a coefficient 1 for a moment, because that will help me easier to multiply my polynomial out. Alright, so multiply two things at a time. Let me show you how to do this one. The first two being multiplied. What I can do, one way is take x times x, x times negative 2, negative I, so on and so forth. Or I can actually look at this two factor a little bit closely. And one of the things that we are learning here is also recognizing certain patterns that can help me to multiply this thing out quickly. What do you see here? There is something going on here that can actually help me tremendously. Now let me give you a hint. Look at x minus 2 together. If I look at x minus 2 together, what this whole thing now look like is a plus b times a minus b. And that actually becomes difference of squares, where my a is x minus 2. Right? Difference of square. A squared minus my b squared. And my b represents I. There you go. Now why would you want to look at it this way? Well, because it will help me multiply these two things out a lot quickly, because now if you know the perfect square binomial, a squared minus 2 times your a times your b, that will be minus 4x, plus your b squared is 4. See? Go from, you don't have to multiply it out if you know the formula. It helps you tremendously here. I don't know if y'all remember what I squared equal to. I squared is actually equal to -1 because I squared means square root of -1 whole thing squared. So square and square root cancels out. I squared equal to -1. So I squared equal to -1, but there's another -1 times in front of it that will make my 1 positive. So the first two multiplied together is actually x squared plus 4x plus 5. Now take that times my x minus 2. And now I will multiply it out. So that will be x squared times x times -2 will be x to the third minus 2x squared. 4x times x times -2, positive 4x squared, minus ax. 5 times x times -2, positive 5x, and -10. Alright, combine like terms, I should get x to the third. Oh, did I do this right? This is x squared times -2 is -2x squared. Sorry about that. -2x squared plus 4x squared, positive 2x squared. Negative ax plus 5x, negative 3x, and minus 10. Okay. Alright, so multiply it out, simplify it, looks something like this. So now, at the very end, it says, I'm also going to have a leading coefficient -4. So that -4 was where? That -4 was up front the whole time. So now I can actually use it now. That -4 was up front the whole time. So multiply every term by -4. My final answer will be -4 x to the third. -4 times 2, -8x squared. Oh man, I'm lefting out my square too much. -4 times -3, positive 12x. And -4 times -10, positive 40. Alright, and that will be my answer. Okay. So, in this lecture video, we talked a little bit about the remainder theorem and the linear factorization theorem. And thank you for watching.